All right, so this is our first lesson on geometric vectors. So again, this course, even though most people, when you think of grade 12, you say, oh, it's the calculus course, vectors kind of gets the shaft a lot of the time, but we're now moving into the vectors portion of the course, and about 1/3 of your final exam will be on vectors. So the stuff we're about to do will be on your final exam. And so we need to make sure we feel comfortable with it so that we do well on that part of the course. So I'm just going to quickly take attendance while we start here. Do you guys ever, I'm sure all of you at this point have seen the movie Despicable Me. Have you guys seen that movie, Despicable Me? The villain in that movie, I don't know if you remember, his name was Vector. And unfortunately, my computer doesn't have sound, but I'm gonna post this little YouTube clip. It's basically of like the introduction of Vector from Despicable Me. But basically, it's like he comes up to Gru, and Gru's like, I don't want anything to do with this kid, but he's like, I'm Vector. I commit crime with what is it? With direction and magnitude. Like that's like his whole spiel about being an evil genius or an evil villain. And so that is what a vector is. It's a quantity that has both magnitude and direction. A scalar is a quantity that describes a magnitude or size only. Okay? So vectors have this associated direction. That's what makes them different from just a scalar number. Okay? So here are a list of 8 different quantities, and we're going to classify them as either scalars or vectors using the definition I just gave. So I'm going to give you, 30 seconds, go through this list and see which ones you think are scalars and which ones are vectors. Remember, scalars are magnitude only. Vectors have a magnitude and a direction. And while you do that, I'm going to take attendance. Your package. Okay. So we're going to fill in the blanks. You're either going to write the word scalar or vector. So a car traveling at 50 kilometers per hour to the east. That's a vector because there's a direction. A child pulling a wagon with a force of 100 newtons at 30 degrees to the horizontal. So the 30 to the horizontal, if you think about it, that is a direction. I'm pulling in a certain direction. It's not just, I don't just care about how much force, I care about the direction of the force. So that's also a vector. A man's mass of 88 kilograms. That's scalar. Mass on its own is a scalar. A woman skiing at a speed of 25 kilometers per hour. Scalar. A parachute is falling at 20 kilometers per hour downward. Vector. Acceleration due to gravity on Earth of 9.8 meters per second squared downward. Vector. The number 5. Scalar. And a person's weight on a bathroom scale. So this is the thing where the word weight actually is used incorrectly a lot. Technically, when you step on a scale and you get a number, that's your mass. Okay, weight actually does have gravity attached to it. I don't know if you like, because will my weight on Earth and my weight somewhere else be different? Like if I was on the moon, right? So something's affecting it. The gravity affects my weight, whereas my mass in both places would be the same. Does that make sense? So It's actually a vector, but that's a bit of a trick question. Okay?
The direction downward.
It would be downward, yeah. And it also means like when you technically when you say a weight, yeah, like it's like the equivalent of speed versus a velocity. A velocity has a direction, but speed it doesn't. It's kind of the same thing. A mass and a mass with direction is a weight. Okay. Now, representations of a vector. So you can represent vectors in different ways. So we just kind of went through some ways of representing in words. Like 4 kilometers at an angle of 38 degrees to the horizontal. So that's one way you can represent a vector. You state a length, a value of the length, and a direction. In a diagram, which is called a geometric vector, it consists of an arrow or directed line segment that shows both the magnitude or size and direction. The length of the arrow represents and is proportional to the vector's magnitude. So when if I draw a vector and I say it's making an angle of 38 degrees to the horizontal, the actual length of this, okay, is representative of a length of 4 kilometers. Meaning that, not that I'm saying that you have to draw everything to scale and you don't have to like take out your rulers and write out like a 4 centimeter line, like a 4 centimeter line segment to indicate this vector. But what I am saying is if that's 4 and then we need to draw a vector of 1, it should be proportional. A vector of 1 kilometer and a vector of 4 shouldn't look identical, right? Because they have different magnitudes. So it's going to be a bit of a comparison game. When you draw pictures, you have to kind of recognize, oh, well, if my vectors are different lengths, I have to make sure that they actually look like they're proportional in the way that they've been written. So 1 to 4, etc. Okay? So that's the visual way of drawing a vector. The dotted line there is just an indicator for the angle, but really the vector is just the green arrow, not the superhero. Okay, so another way of representing a vector is in symbols. So in symbols, we can use the end points of the arrow. So notice that the vector here, it starts at A and ends at B. The arrow is at B, so we call it the vector AB. Now the photocopy might not have clearly shown this, guys, but what this is like a little arrow on top of AB. Okay. Sometimes when we're doing it, like you're doing it in your notes, just to save time, sometimes we just go, when we're writing it in our notes, we kind of just throw the upper half of the arrow on just to save us some time. Because if you're going to be writing a bunch of vectors, it might be a little bit tedious to have to always draw a full arrow with 2 strokes, whereas that's a way of kind of indicating an arrow with just using your 1 pen stroke or 1 pencil stroke. Okay? And then the terminology is important to recognize that where a vector starts and where a vector ends is important. It's not like, who cares where the A is and the B is. Once you've drawn a picture of it, there's a specific reference of what the A means and what the B means. So point A is the starting or initial point of the vector, also known as the tail. Okay, it's the end of the vector. Okay. Point B is the head or terminal point of the vector, also known as the tip or the head of the vector. Okay? So that's vector AB. And then in some cases, we can just refer to a vector, instead of using its head and tail capital letters, we can just refer to the vector as a lowercase vector with a symbol on it. So we could refer to this as vector AB. We can also say it's vector V. Usually when we do this, it's lowercase. So capital, if I'm using capital letters, it's head to tail to head. If I use lowercase, it's just an indicator that, see this vector here, it's vector V. Okay? And, so those are different ways you can represent a vector. And depending on what context you're in, you might want to choose one way versus a different way. The magnitude, okay, so we've already said that word today. The magnitude, length or size of a vector is designated by using the absolute value bracket. So you know how absolute value bars, okay? As soon as you put absolute value bars around a symbol that means a vector, now I only care about the length of it. I don't care about the direction. I just want the magnitude. It's a way for us to work numerically with vectors. Because a vector, I want you to be very clear from the very beginning, vectors have directions. But it's hard to, add directions and, or multiply directions or do different operations with directions. But I can do it with the number part. And so I want to be able to separate the number part of the vector from the entire vector. By putting bars around it, I'm indicating just the length. Okay? So if you have the vector A, B, or V, you just put the bars around it, and now it's the magnitude of vector A, B, and the magnitude of vector V. Okay. There's a lot of terminology today. Okay, so keep going with me here. So a vector's direction can be expressed using several different methods. So one way is it can be an angle measured clockwise or counterclockwise from a horizontal or vertical line. So do we all know what clockwise versus counterclockwise is, guys? So if you are told draw a vector that is 30 degrees counterclockwise from the horizontal and has a magnitude of 5 units or 5 centimeters or whatever, then you draw a horizontal. So like get used to just doing a dotted line to indicate these horizontal or verticals. If I want to draw something 30 degrees counterclockwise means going backwards around a clock, right? So the hands would be going backwards, okay? So I have just drawn a vector that's 30 degrees counterclockwise from the horizontal and is 5 centimeters long. If I said draw a vector that's 5 centimeters long and 30 degrees clockwise from the horizontal, then instead of the angle going upwards, it would have gone downwards. Okay? If I have from the vertical, so you could have a vertical line, and I say draw a vector that is, 30 degrees clockwise, 30 degrees clockwise from the vertical, that would be an example of something that's 30 degrees clockwise from the vertical. So you draw a vertical line, draw a line segment that's about 30 degrees to the right, and indicate its magnitude. And now I've just drawn a vector that has that representation. You guys get that without that dotted line, though, it's hard to tell what the direction is, right? So that's the little dotted line with the little arrow with the angle is going to be an important piece of the drawing. Because I think we can all agree, if I just draw this without any information, what does that mean? It's like you don't know the direction. You can't tell the direction from that, whereas if I keep that in, now I know the direction. I have a reference. And that's from the horizontal and vertical, but can you also see this could also come into play with like north, south, east, west as well. So that's the next thing, right? Well, there's true bearings first. Now, true bearings, I think they introduced these to you in grade 11. And then they kind of throw them at you, and then they say, and bye-bye. Like, we don't really see them all that much. And you might have seen it in physics. How many people have taken physics before? You talk about true bearings, like clockwise from north. So like, if I just say, so a true bearing is a compass measurement where the angle is measured from north in a clockwise direction. So, for example, if I said draw me a vector with a bearing of 100 degrees. So without me telling you anything else, if I just say bearing 100, or I say true bearing of 100, what you have to interpret that as being is that north is 0 degrees, okay? So there's north. What would be east according to this rule? East would be what bearing? If true bearings are measured north in a clockwise direction. If I went east, what would be the bearing that would be, I would be drawing a vector due east. So it would be a horizontal vector going east. It would be if they told me the true bearing was 90. Does that make sense? So 90 would be exactly east. So 100 must be an additional 10 degrees. Okay, so this would be 100 and 100 degrees, 90 plus 10. Okay, and that would be a vector that's going on a bearing of 100 degrees. Okay. If I said draw me a vector with a bearing of 300 degrees. So let's think about that one. And this is where I might draw all 4 compass quadrants this time. So this is north, and I want to go 300. Think of it, I'm spinning my arrow clockwise from north. When I hit 90 degrees, I'm heading east. I go another 90 degrees, I'm going to be heading south. So a bearing of 180 would be south. What would bearing, if I want to go west, what's the bearing west? Back over, I know it's been a while since we've been back to degrees, but embrace the degrees. We're back in degree mode here. 270. So 300 is plus 30. So we're now, but you guys get that this is the angle 300. Okay? And that would be a vector that goes in, it's actually going in a northwesterly direction of some degree, but that is how you would draw it if you're told a bearing of 300. If you're told true bearings, it's your basic clue that it's a true bearing is it's an angle, but they don't put the north and the south, east, west. They don't put those indicators. And if it's quadrant 1, typically they actually will say like 040, like 040. And like I don't know if you've ever like on like TV shows, it's like we're going on a bearing 040. You know, that's like 40 degrees. Like they're using true bearings. Okay, so they're kind of just indicating from north. All right. They come up here and there, so that's why I'm talking about it. The one that you're probably more familiar with is this third option. The third option is a quadrant bearing, measurement of an angle between 0 and 90 degrees east or west of the north-south line. So I want you to look at this picture, the 2 pictures we just did here. So this angle here, this 100-degree angle, okay, do you kind of see that it's in a quadrant that's in the southeast quadrant? Is there a way you could reference south and east and this vector to indicate its direction without having to go clockwise from north? Can you reference using east and south a way of saying what the direction of the vector in the first picture here is? So like in this quadrant, if you all agree 100 degrees is not in this quadrant, right? It's only a little bit of the angles in this quadrant. How much of the angle is in this quadrant, this southeast quadrant? Just this little 10-degree piece, right? So there's 2 ways you could say it, and they're both technically correct. They're both technically, I would give you a mark for it. But usually we start with the north-south, and then we go east-west afterwards. Okay, so if I said, tell me the direction of this vector, you can say, well, head south and go how many degrees towards the east? South, 80 degrees east. Would that be the rest of the angle there, guys? Because in total, it would be a 90-degree angle, right? So south, 80 degrees east, east, 10 degrees south. Both of those are equivalent. But conventionally, we usually start with north-south. Okay, so if I said draw a vector, so on a bearing south 80 degrees east. Does that ring a bell? Writing a bearing like that. Do you get this? A picture is going to be identical to the one above. I draw it in a little bit different way. So north. But I say, okay, I'm going to draw this angle. So the first direction tells me to start going in that direction. Start going south. Then go 80 degrees and towards the east direction. So south, and I want to go 80 degrees towards the east. So that would be my vector. Okay? So using that same logic, what would the 300 degree one be? The 300, remember we said that by the time you get to west, what was the angle? We've gone 3/4 of the way around from north, and that was how many degrees? 270. So the additional little bit of angle over here is how much of an angle? Just 30. So again, starting from north, what would be the angle here, guys? North, how many degrees west? North, 60 degrees west. Very good. So that would be, if I said north, 60 degrees west, this is saying start pointing north, go 60 degrees. Go 60 degrees towards the west, and that was where your arrow, where you're going to draw your vector. Okay. So the whole point of me choosing those two examples is the pictures in those two should look the same. The way that the bearing was stated is different. Okay? It's really important to get this straight because eventually we're going to be adding vectors and we're going to have to understand how to draw them so that when we add them, we add with the correct angles. Okay? Like just foreshadowing to a little bit later this week, guys. If I wanted to add like two vectors, do you guys get that it's going to be really important to understand what angles are they ending at and starting at, because that's how we're going to be able to tell how to add them. Okay? We'll get to that a little bit later on this week. Okay, so far so good. Those are bearings. So let's just practice stating vectors in words given a picture. So here's a picture of a vector, or 3 vectors actually, and I want you to look at the way that the information has been provided, and hopefully you recognize that one of each type that we just discussed is present here. So let's properly state the vector using each of those kind of what's indicated by the picture. So in A, how would we describe that vector in words? First of all, what would we call the vector in A? Vector PQ. So vector PQ. So in words, what does a vector, what are the two pieces a vector has, guys? Of magnitude and a direction. Do we know that vector's magnitude? So vector PQ has a magnitude of 14 centimeters and a direction of, how would you describe the direction? So I see an angle. Okay, so you're almost there, 100 degrees from the horizontal. We just have to be specific about which way from the horizontal. Is it clockwise or counterclockwise? Going away, like if you're thinking about the hand of a clock, it's going, the vector from the horizontal that's drawn here, it's going counterclockwise. So of 110 degrees. So you can write counterclockwise long form, or I'm okay with CCW, counterclockwise, as the short form. What do you think the short form for clockwise would be? Just CW, okay? So counterclockwise from the horizontal. Okay? in B, so notice the way they've named this vector. They don't have a tail and head labeled with capitals. They just have a lowercase, so that's what we gotta call it. So we're gonna call it vector U. Okay. So the same similar way has a magnitude of, in this picture, it's obvious the magnitude is.
Excuse the interruption. Would our teachers please send down your period to attendance? Thank you.
A magnitude of 2.3 kilometers. And instead of saying a direction, I'm just going to say maybe in this case, as soon as you see a north, like a north reference, maybe don't call it a direction, we say a bearing. And this time, is it going to be a quadrant bearing or a true bearing? Because do we see that arrow? Where's that arrow starting? It's starting at north. So we're going to say, and a bearing. If you want to say true bearing, you can, but it will be understood when you write the number here that it is a true bearing, because you're not going to include the N or the or S or E and W. You're just going to say an angle. And what angle are we going to say? 135. You just literally say the angle clockwise from north. You just plug it in there. Again, I'll just say this again. If the vector happens to be in quadrant 1, we usually include a leading 0. So what I mean by that is if this vector, so don't draw this, but if this vector had been like that, we would have actually done this. It's just the way you kind of still, you're clear it's a true bearing. You always use a 3-digit angle. Think of it like that. It's always a 3-digit angle. You would use a leading 0 if required. Okay? Just to let you know. When you see that in the homework, don't freak out. There's like, why are there zeros in front? That's weird. It's because that's the way a true bearing looks. Okay, and then in this last one, this one, do we see that the first part's going to be very similar, vector V, magnitude 9.8 newtons, but notice this time the angle is referenced just to south, okay, and an arrow going into towards west, so this one's going to be, vector V has a magnitude of 9.8 newtons and a bearing of, so this time we're going to use a quadrant bearing. So start with a direction, write an angle, and end with another direction. So what's the starting direction here, guys? South. Okay. And then it goes 35 degrees towards the west. Okay. Okay. Good. So that's how bearings work. Okay. Okay, we're going to become artistes now. You ready? We're going to draw some vectors. If you do not have a ruler or a straight edge, you 100% need one for this unit, guys. So if it's disappeared, go to Dollarama, buy a ruler, or have a ruler, okay? Rulers are important for this unit. The last thing I need is for your vectors to start like being all curvy, okay? Vectors are directed line segments, they are not curves, okay? So, draw a geometric vector with each bearing. Show the scale you used on each diagram. So they want you, again, they really want you not to just be using like a straight edge. They would like it to be you using some sort of scale based on your ruler. Okay, so for example, so in A it says vector V equals 2 kilometers at a bearing of 020 degrees. So there's that 3-digit bearing again. So let's start by drawing a north and in. Is everyone okay that I really only need, maybe you don't even need the east, but I only really need a north 100% to be able to draw this. Okay? So, let's start by saying, so I need a bearing of 020 degrees. Now you might be listening, we talk about rulers, and if we're to be completely honest with ourselves, we really should need another lovely geometry tool that comes with those good old geometry sets. Good old protractors. You guys remember good old protractors? Remember how they work? You line it up, find your 20 degrees. Okay. So here's the deal. I am not going to be checking your work with a protractor. As much as I would love to spend my life measuring all your angles, sorry, not happening. So, but here's the deal. You need to, to the best of your ability, try and draw as accurate as you can what you think a 20 degree looks like. 20 degrees should not look like 90 degrees, right? And everyone here should have in their mind what 45 looks like, halfway. And so play the game in your mind, okay, well 20 would be less than half of that. So that's the game I would be playing to come up with the 20 degrees. And once you made that decision, you're gonna go you're gonna go 2 kilometers. So what would be, if you're using a ruler, what would probably make sense here? 2 centimeters. So if you take your ruler, please don't do 2 millimeters. Okay, 2 centimeters would be good. I don't think we want to do 20 centimeters unless you want your lines to go into like the words and stuff. So a 2 centimeter line, and then again, your idea here is 20 is going to be something like this. Because 45 is like this. You see what I'm saying? Like you have to kind of eyeball it. And I'm going to write 2 kilometers next to this. And I'm going to write a 20 degrees next to that. And that is what I'm looking for picture-wise. And then it says show the scale you use. So you're just going to say like 1 centimeter is equal to 1 kilometer. That's like your little good old legend. Remember legends? So like grade 9 geography. Fun time. Okay. And the other thing I should maybe do is call it vector B. So there it is. I have drawn the vector. And as you can see, I can leave the east line, but I don't really need the east line when it's a true bearing. Yeah. So in B, we've got vector U equals 40 kilometers per hour, south 70 degrees west. So this time, when I do my setup here, what should I be drawing? What kind, like should I focus, do I just need to worry about north, or should I have some more directions? Should I draw all 4 quadrants maybe just to be clear? Hopefully we've all know our directions. Anyone directionally challenged here? Never eat shredded wheat. You guys all know that stuff. Okay. Never eat shredded wheat.
Never eat sour watermelon.
Oh.
And that's how
Okay. So I guess because shredded wheat is actually healthy for
never
you.
eat seaweed.
Oh, okay. All right. Anyways, so the idea here is I need to draw a 40 kilometer per hour vector. Hello, sir.
Just a quick question, Michael. Could you come give me period 3A? I seem like you have something important here, so I don't want to interrupt.
Oh, no problem.
3A? Okay, from Mr. Richard, first get your message.
Lovely, thank you.
Okay. So the idea here is south 70 degrees west is the direction. You guys get that kind of is your first go-to. The drawing of the vector will we need to do that once we figure out what direction we're going, right? So where would south 70 degrees to west be? So again, let's interpret that bearing. The first direction I see is south, so I should like kind of start my pen facing south. And then it says 70 degrees west. So that means that my vector needs to go a lot towards west, right? 70 degrees. So that when I draw my vector, okay, I'm going to draw the 70 degrees like this. And I'm going to write 40 kilometers per hour. Now, for you guys, in this case, what would maybe make sense in terms of your scale? You could say 1 centimeter is 20 kilometers per hour. And then if you did that, would those vectors actually be the same length? You guys kind of see what I'm saying there? So if I did 1 centimeter is 20 kilometers per hour, that would be a situation where the vector I just drew is basically the same length as the other vector. Okay? That would be a 2 centimeter long vector. Okay? Just to match it to over there, I think I would have done this a little bit longer. Okay? Whereas if you did 1 centimeter is 1 centimeter is 10 kilometers per hour, then you have a 4 centimeter long. Right? You said 1 centimeter is 40 kilometers per hour, then you have a 1 centimeter long. Like you can make it match as long as you tell me your scale, you can kind of make your own choice there. Yeah, you bet. Okay. Okay. So far so good? Okay. All right. So now we're just going to practice converting from one type of bearing to the other, just to practice. So write the true bearing 150 degrees as a quadrant bearing. I want you to draw the write the true bearing as a quadrant bearing. If it helps, guys, draw it out. Where would 150 be? So true bearing 150. So again, clockwise from north. Okay, so clockwise from north. I always like to count by 90s to kind of get a feel for this, right? So if I'm at north and I go a bearing of 90, I'd be east. If I do 180, I'd be south. Uh-oh, I went too far. Can you guys see my logic there? So you guys get, I'm going to be facing down in this quadrant down here in the southeast quadrant. And how far into this quadrant did my vector go? So if this is my 150 degree bearing.
Why is it not bad?
Because true bearings are always clockwise from north. You may do this that way. True bearings, whenever you just see a bearing that's just a 3-digit bearing, it says true bearing is clockwise from north. So I bypass east. And how much into the next quadrant do I go? I go an extra 60 degrees. So again, I'm not going to take a mark off. You could start with east and then say east a certain degree and then south. I just think it's nicer to start with south and then go east. And I don't know, you have to talk to like Mr. Mayon or Mr. Spatafor about the rules there if it really matters. I don't know. Do they care? Have you done this before with vectors?
Not for bearings. I don't know which ski it is, but
Yeah, I've never heard of that.
Okay. Well, so I'm going to go with the quadrant bearing. So now I'm doing the quadrant bearing. So I'm going to start with south. And if I start with south, then it's the same vector, but if I'm coming from this direction, what's the angle? South, what degree east? 30, right? South 30 degrees east is the same thing as east 60 degrees south, but it's cleaner, it's more accepted, it's more conventional. You start with north south and let east west be the second number, the second direction. And then I'm probably not 100% correct because I'm sure the textbook's going to do east south sometimes, so don't freak out. Either is correct, but I think it's just nicer to start with the north south line. Michael, I think you have a visitor. I think you have a visitor. Can you talk to Michael?
Thank you.
Okay. So now go the other direction, literally. Okay. So write the quadrant bearing north 50 degrees west as a true bearing. So now we're going to go the other way. So if I draw north 50 degrees west, north 50 degrees west is looking like this. North 50 degrees west. There's my vector that's going north 50 degrees west. If I want the true bearing there, true bearing, again, what's the true bearing? I draw true bearings, what's the rule? From clockwise from north. So I need this angle. That's the true bearing from north. It's going to be 3 digits. what are the 3 digits if I go all the way clockwise from north and I get to that same vector location? What angle is it? Well, if I get to west, what angle is it? 270. And then into this quadrant here, 50 is taken up on this side, so this side must be 40. So putting it together, 270 and 40, that's 300 and that's the true bearing. So that's converting quadrant bearing to true bearing to quadrant bearing. Okay? So the last thing we're talking about is some more terminology because you just can't get enough of it. And this will come up in the homework. It's going to seem a little silly and easy, but just take it for what it is. Right now, I think you can all appreciate some silly and easy stuff, right? So parallel vectors are vectors that have the same or opposite direction, but not necessarily the same magnitude. So if you're parallel vectors, you don't have to be the same size, but you just have to have the same or opposite direction. So if you just make a choice on your paper, guys, and draw a vector with your ruler. Just draw one. And then the key here is just slide your ruler along a little bit. So don't try and keep it going in the same direction. And draw a vector that's going in the same direction, but just has a little different size. So I'm going to draw this vector. I just drew parallel vectors. And wait a second, guys. What if I do this? Still parallel. The opposite direction still counts as parallel. So I have just drawn some parallel vectors. Okay? You go and do some little artiste work. Okay? Okay, ready for another one? Another new terminology of vectors. Here's another one. Okay. Hello. Sure. So, equivalent or equal vectors. Okay, equivalent or equal. So either of those terminologies. Equivalent or equal vectors have the same magnitude and the same direction, but the location of the vectors does not matter as long as wherever they start and wherever they end, they have the same magnitude and direction. So what that's saying is, again, let's draw random vector. And now I can do this, but you can't, so haha, but okay. I just created an equal vector. Because what is it? It can start at a different location, but has the same magnitude and same direction. That if I place this, maybe I'll change its color just to show it it's different. Orange. Okay. So you guys see they're the same, except they're same in length, magnitude, same in direction. They're pointing in the same direction. So we consider them to be equal. It's important to recognize this because eventually, guys, we're going to start creating shapes with vectors. And if we create shapes with vectors that are equal, then we can, use our knowledge of, you'll see as we build our knowledge of vectors throughout this unit, we can start doing some actual mathematics or arithmetic with these vectors. But equal vectors have the same magnitude and same direction. Okay? Has to be both of those things to be equal. Okay? The last terminology of the day is opposite vectors. Opposite vectors have the same magnitude, but, oh my gosh, this is so out of the blue, they are opposite in direction. Opposite vectors, opposite direction, okay? So the location of the vectors doesn't matter, again. So I could pretty much take these same two vectors, here I'll draw it again. So I'm going to draw, here's a vector, okay? I'm going to clone this vector. Right now, this vector that I just created, I'll make it, well, I'll stick with orange. Okay, so right now these are equal vectors, they are not opposites, okay? Like these would be equal. But if I do this, okay, you guys get now they're opposites, okay? Opposite, because now that they're the equal in length but opposite in direction are opposite vectors. And this is again gonna come into play when we start doing operations, because I want you to think, what do you think happens if you add two vectors that are opposite? If you go, I say, go along the blue vector and then go along the orange vector, that's like adding both vectors, what happens? You go back to where you started, and you end up going nowhere, okay? So that's going to come into play, opposite vectors. Okay? So that is that's a very like wordy lesson and easy lesson. This is just a summary of all the things we just talked about. There's a few questions there. Most of them are kind of easy, so take it as a nice little kind of brain break, okay? Just do the questions though, because you don't want to mess up easy questions when harder ones are coming soon, okay? So thank you for listening, and we continue tomorrow.